All right, line S1, we're going to take a look at learning task number 1, which is going to be us describing common HVAC systems. HVAC stands for heating, ventilation, and air control. And it's just going to be our basic methods that we are going to go and heat houses, industrial premises, and things like that. So let's start by going through the first one that we're going to be very familiar with, which is going to be a baseboard heater and thermostat that we are going to have over here. We'll start with the control, then we'll talk about the second component, the baseboard. The control for these is going to be a thermostat. Now, we have heard the term thermostat. Thermostat is a temperature-actuated switch. It responds to temperature, and it can either be a normally closed thermostat that is going to go and open, or a normally open thermostat that is going to go and close. We refer to these as heating or as cooling types of thermostats. A cooling type of thermostat is going to close as the temperature would go and rise. We would draw that one out to look like this. This is our standard symbology for a thermostat. And a heating one would look like this over here. That little symbol on the bottom indicates the fact that we have got temperature response for these. And what we always do is we always look at the rise in temperature as if the temperature is rising, that it was going to go and push up on these. This one over here would make sense that we would want to go and place this thing through to a heat source, because as the temperature would be rising, eventually it would get hot enough and then it would open that circuit, shutting that heater off. And then if it would start to cool, the temperature would fall and then our heat would go and turn on. This one over here we would use for a cooling type of system, because we would see that as the temperature rises, it's eventually going to go and kick this switch. It's going to hit that switch. When it hits that switch, it closes and activates our cooling type of system that we will have. Either one of these is going to be our standard symbol. Understand how the symbols are going to be different, for our heat one, which is going to the top, versus our cooling one, which is going to be going down to the bottom. They're very similar looking, but it's an entirely different operation just based upon where that one line is going to be laid out. Let's talk about what's inside of the picture over here. Inside of our picture, they're showing us a thermostat that is termed as being a DPST. Now, a DPST stands for double pole, single throw. In other words, when we throw the switch, it can either stay in the open position or the closed position. A double throw would mean that it would go from a single position to an off position to another position. We go through multiple modes. This one's only got a single throw that's going to be on it. Thermostats are going to go and automatically turn on and off our baseboard heater. Usually they're going to involve a little spring-controlled micro switch inside there that's going to be toggled by some other type of element, a bimetallic strip being our most common one that we will utilize on these. If the thermostat breaks both lines for a 240 volt type of system, we are allowed by Canadian Electrical Code to have a marked off position on it. But most of our thermostats that we are going to see out there are not going to have that. What we usually see is thermostats, and for those of you that have ever installed these before, you know that you're usually only breaking one line, which means that I've got a constant 240 volt. This over here is my line 1, this over here is going to be my line 2, and inside of my thermostat, I'm only going to be breaking a single line, which means that it is always live inside of here. You can never rely on a thermostat as your disconnecting means before you work on a baseboard. If there's a baseboard that's not working, don't just turn it off at the thermostat. You actually got to throw the breaker unless the thermostat has got that marked off position. If it has a marked off position, then you know that it must be one of these where it's going to be breaking both lines inside of there. We do have some other types of thermostats as well that are going to be what we refer to as low voltage types. Generally used for large amperages. So not just a standard baseboard that we'd be looking at, but usually like a large unit heater or some other component, where what we'll do is we will come in our actual components over here. Oftentimes are going to go and control the amount of voltage we're going to step down. They're going to have a control relay that's going to be inside of there, and then they're going to have a low voltage thermostat itself. This is seen as just a control board. It can sometimes be built into the units itself. Other times it is going to be just a separate thing where we have terminals. Over here we would see line 1 and line 2 terminals that we would have over here. And on the other side we would see T1 and T2 terminals. That indicates the load. L's are lines, T's are loads when it comes to control devices. And then we would usually go and have a TS. That is just going to be these ones here. And it's just going to stand for where my thermostat itself is actually going to go. bring my lines into this side of the device, bring my loads out of that side of the device, and then I just connect a low voltage wire over to my thermostat itself. Allows it to go longer distances. You don't have to have as much, worries about cabling, etc. I don't know if you've ever been inside of a commercial building. Lots of commercial buildings have got low voltage HVAC controls, and a big reason for this is that it can be run all over the place inside of the plenum. That's going to be the hollow space above the T-bar ceiling. If you ever poked your head up inside there, you know that all of your cables and all of your conduits are strapped nice and neat to the surface, but then that the low voltage wires are just kind of run just loosey-goosey all over the place inside of there, just from place to place. And so it's a big benefit for speed and ease of use, when you can start utilizing some of that low voltage wiring because you don't have the same restrictions. That's why people like to use these. Whatever type of thermostat you are going to use, whether it's going to be single pole, single throw, which is going to be our standard ones, whether it's going to be one of these marked off double pole single throw, or whether it's going to be low voltage, you want to make sure that those are always going to be mounted inside of the room away from the heater itself. The heater is going to be on the outside wall. We'll talk about that inside of in a second over there. But the thermostat you want to have opposite. You don't want to have this thing directly over top of any heating ducts or close to any light bulbs or anything like that that are going to produce a lot of heat, or where you're going to have direct sunlight on it, because obviously all of those are just sources of heat that are going to cause erratic operation of it. Let's talk about the way that these things are going to go and mix. Not yet about that. Let's start first by defining what a baseboard heater is. A baseboard heater is simply going to be a chunk of highly resistive wire, right? R is equal to K times L over top of CMA. And so what we have inside of here, if you've ever opened one of these up, by now hopefully everybody has done one or two of these, you'll see that across the back plane over here, there's going to be this thing that's got all these little fine aluminum fins. The reason we've got all those fine aluminum fins is because aluminum carries heat very well, and heat always moves from areas that are hot to areas that are going to be cool. It's basic, laws of thermodynamics. What we have inside of those fins is there's going to be a ceramic tube, so I'll just draw this out over here. We're going to go and have a long ceramic tube, and in the very center of that ceramic tube, there is going to be a nichrome wire. Sometimes it's coiled, sometimes it's not, but that nichrome wire just goes through the inside of the ceramic tube. The ceramic tube is designed to go and be the insulator and the support for it, so you can touch those fins. Those fins are literally just sitting around the ceramic tube. You don't have to worry about getting a shock off of those fins because they have no contact with the wire that's on the inside. We'd have so many dead children if we did otherwise, because they always stick their fingers and stuff inside of these baseboards. There's absolutely no way that any of those fins could ever be live. They could be hot, they could burn you, but they're not going to shock you or anything like that. So the ceramic tube has got the nichrome wire inside. The nichrome wire is going to have a fairly high amount of resistance to it, and we are going to be able to dissipate a lot of heat off it. We carry the heat from the nichrome through the ceramic, which isn't awesome, but we need it for the insulation and for the support, and then out to these actual fins, and then these fins will radiate that to the air itself. Usually we are going to go and have these inside of zones, smaller zones. You don't heat massive spaces with these in most cases. You have far more efficient methods. If it's the only thing available, if there's no gas on site, sometimes we will use them inside of large houses, etc. But usually baseboards themselves are going to be confined to small areas. We will refer to them inside of the code as individual thermostatically controlled devices. Very common way that the code will go and refer to these, where they're going to talk about each area or room is going to be controlled by an individually thermostatically controlled device. And usually they're going to be talking about electric space heating or baseboard heating at that point. We'll take a look at that inside of code this week. We'll cover through some of that. Baseboard heaters have two densities that they are going to go and have. There's going to be density that is considered to be standard density, and then there's going to be high density. High density changes from manufacturer to manufacturer, but low density, or what we are usually going to deal with, standard density, I guess I should call it, is going to be 250 watts per foot. So basically, if you have got a 4-foot heater, you've got 250 plus 250 plus 250 plus 250. That's going to be 1,000 watts. If you know the size of the room that you need to go and heat, and you need to go and have, a 1200 watt heater inside of that room, what you would have to do is you would just take that 1200 watts, divide it by 250, which would equal to, 4.8, I guess, is what it would equal to. So you would need to have at least 5 sections. In other words, you would need to go and have something that is going to be at least 5 feet long. So you're going to be looking to mount that onto a wall space that's going to be at least 5 feet. Standard density of this 250 watts per feet is going to be very, very useful for you if you ever start doing your own layouts. A lot of times right now in your apprenticeship, it's second year, you're told what to do and where to place stuff. But when it comes, time that you're going to start taking on and running some of these smaller jobs, initially it's going to be a little bit of a pain trying to sort out your baseboards. Remember that 250 watts per foot as a standard density. And if you miscalculate, you don't have enough room, you can always get some high density. Sometimes they just end up being a long order or something like that. They are going to go and start from 500 watts, which is going to be our lowest one, and then we are going to move up from that 500 watts, usually at 250 at a time, that we are going to go and have. Voltages for these ones are going to be generally higher is better, because we know that watts are equal to my I times my E. So if I go to a higher value of voltage for the same amount of watts, I go to a lower value of current, and then we can get away with smaller conductors that are going to be run out to each one of these components. So we do like to go line to line values of voltage. Generally speaking, that's going to be 240, 208, 600 volts is out there, 480 volts is out there, but they're less common. Less commonly, we will go line to neutral. 120 volts, 277 volts, 347 volts. Those are all going to be line to neutral voltages that we don't use as often. For installation on a baseboard, what we want to do is we want to go and identify the area that is going to be the coolest. Okay, so we're going to go and find an area that's going to be coolest. Over here, I've got an exposed exterior wall. The rest of this over here is the inside of my house, so I'm going to go and have somewhat heated air that's going to be inside of these. What we do is we find the cold one, and then we want to find the coldest spot that is going to be on that wall. And the reason for it is not because we're going to be trying to bleed air to the outside to heat the universe, okay? It's really counterintuitive. Sometimes people say, well, I don't want to put it below that window, because then if I put it below the window, it's going to go and cause me to lose all of this heat. What's actually happening is that the air is going to be falling at our coolest place. When air cools down, it literally falls. If you go online, you can Google YouTube videos that are going to show just thermal cameras where you can see air currents, visible air currents. And what you'll see is that if I have got cold air, that cold air is going to go and fall down from the coldest spot. It cools the air, that air drops. In the meantime, I'm going to go and have hot air that is going to be rising from my baseboard, and as soon as I get two streams that are going to run into each other, this stream of hot air, this stream of cold air, those two are going to mix, and then they are going to go and tumble, and they push out because they're both trying to push. They can't push back up against the wall, so they're going to have to push out and across the room. Makes your whole room much more comfortable, obviously. You don't feel it. It's not like it's a massive, massive air current or anything like that. You used to be able to, I don't know if anybody here smokes, but when I used to smoke, if you had a cigarette and you were right near a wall, you could actually see your smoke pushing away from the wall, because you would go and see that cold air would be pushing down and driving that thing over. Just a small little bit of heated air, but it's a visible area when you got smoke off of something, right? If we don't do that, if we do that thing where we're like, well, I don't want to heat the outside world, and I'm going to put this thing on an inside wall, so that would be placing it incorrectly, someplace like this, which is a bad placement. If I am going to go and do that, my hot air is going to go and rise, and there's nothing for it to go and run into. So it's going to go and heat up the top. My cold air is going to go down to the bottom over here. And what we're going to do is we're going to go and form this line. It's called the thermocline. I don't know if any of you fish at all, but if you've got a fish finder, ever been on a boat with one, you're going to see that one line partway through the water column where, the two heats kind of have separated, whatever the water temperatures are going to be. We call that the thermocline. The thermocline exists inside of rooms as well. If we would do this, we would end up with uncomfortable heat up top, and we would end up with a lot of coolness down here below. So just when you are doing your placement, place them in the area that is going to go and be the coolest, because the coolest area is going to then cause us to go and mix and push that air across the room. Over here for this baseboard that it makes sense to have the thermostat right next to the door. You would be better served for temperature regulation to have the thermostat all the way over here, but the problem with that is it's going to be behind the door, and usually you want to go and keep your controls for a room close to where people are going to enter and exit. So it's not the most effective as far as a heating standpoint is concerned, but as far as a usability, this is a great spot to go and place your thermostats right next to the door. Industrial units will go and use different types of heaters. We will go and refer to the term unit heaters. Unit heaters can either be gas-fired or they can be electrical. In here, we're going to talk about electric ones right now because we're still going through the electric heating ones, but the gas-fired ones will look very similar. They're just going to go and have a set of burners, and what they will have inside of them is a heating element of some sort, and then they're going to have a fan to go and push stuff through. Sometimes you can toggle the fan without having the heat turned on as well, but the fan force itself just allows you to go and move that air much quicker throughout an area. What you do want to do with these, if you are setting them up, is you want to go and set them up inside of a racetrack type of configuration, where the air from this is going to go and hit this, and then it's going to go and get a boost. I don't know if you ever played Mario Kart. There's all those little speed boosts on the track. You imagine them like that. It's going to slow down, and then it's going to get a boost, and it's going to push through, slow down, and get a boost, and push through. And so we want all of the air to do that. That's picking up and then getting reheated and pushed back out. You never want them in opposition to each other because it ends up with weird, warm and cold spots based upon the room geometry. Do make sure if you are using these that you are mounting them far enough away because they do push heated air. If you have anything that like a beam that goes across the room here, you could run into problems where you're going to be pushing too much heat up against this beam over here. You're going to raise that temperature of the beam to over 90 degrees, which is outlawed by our Canadian Electrical Code. Okay, electric furnaces. Electric furnaces are fairly rare. There was a point back in, I think it was the early 90s, that these things were going in for just a little bit because gas prices were high at that point. They were having trouble with extraction, and then after that they kind of figured that out and went back to, gas being cheaper. We can get more BTUs out of gas than what we can out of electricity for, equivalent dollar amount. So we don't have a lot of them. What they are going to be is just basically an accumulation of baseboard heating elements. That's what all of these are over here. We're going to have a whole pile of these that are going to be inside of there, and then we are going to go and have a fan that is going to go and take air from the rest of my house, and then it's going to go and heat that air up and then push it out to other areas. And instead of turning on all the elements at once, what we're able to do is we are able to go and turn on just a couple elements based upon, what the incoming temperature is and what the outgoing temperature is going to be. So what we read off of our wall thermostat is going to go and turn this thing on and off. This thing is usually going to have more than one temperature sensing element. Usually we have one on the inside as well on the incoming air. We'll sense what the temperature is coming into there. We'll sense what the temperature is coming back out of there. But we're going to go and say, based upon the temperature that's coming in here and what I desire to heat it to, I'm going to go and turn on, 1, 2, or 3, 4 elements inside of these things. They are going to be massive, massive electrical demands that they are going to have. They're also always going to go and be line voltage as well. And they can be a little bit tricky, to deal with any sort of troubleshooting on them. For an electric furnace, the one huge benefit is that they do not need to have any sort of an exhausting type of system. For a regular furnace, we have got products of combustion, all the carbon monoxide and smoke that happens whenever we burn natural gas. We need to get rid of that or else we would poison everybody inside of that house. So we need to go and have ducting and, exits to the outside, etc. These over here do not require that, so you can mount them pretty much anywhere. It makes them really easy to place into installation for that reason. Okay, let's talk about gas-fired furnaces. Gas-fired furnaces are going to be probably the most common way that we heat any sort of single-family dwelling. In multi-family dwellings, apartments, and things like that, we don't do a lot of these because usually that would involve us having to run ducts through the ceiling, and usually what we want to have inside of our ceilings and walls is we want to have a thick barrier of insulation and soundproofing. You don't want to hear what the people on the floor above you are doing or what your neighbors are doing. You want to kind of feel like it's your own suite that you're inside of. So those will usually be electric heated, but if you're going to be a standalone residential building, most of those are going to be done through a furnace. The furnace is going to be mounted usually inside of the lowest point of the house. If the house has a basement or crawl space, it'll go down there. If it is going to go into a single floor, it's obviously going to have to be on the single floor, but you want to go into the lowest one because heat tends to go and rise. And so you're going to go and utilize that so you don't have to push the air as much. If I were to mount my furnace all the way up top, I would have to go and push back against the rising air to force it down to other areas of the house. So we place these things low. What we then do is we are going to go and have an intake and an outflow. So we have got what we call supply and return. Return is going to be this duct over here. And that duct, all that it's doing is it is taking in air that's going to be inside of my house, and it's going to go and run it through the furnace. Inside of the furnace over here, there's going to be a place where that cold air is then going to be able to get heated. We'll talk about the components of that in a second. As it gets heated, it is then going to go and return into what we call the supply ducts, and then the supply ducts are going to feed that back out into the rest of our house over here. Put them up there, put them up there, etc. So we are always going to go and have supply ducts that are going to be pushing it out. Once again, the supply ducts, even though they are pushed by the furnace fan itself that's going to be down inside of there, you do want to place them on areas of heat loss up against those walls so that once again, anything that these are pushing up is going to get counteracted by any cold air falling down, and we're going to get better mixing throughout our rooms once again. There is going to have to be this exhaust that we are going to need as well to get rid of our products of combustion. And we also don't want to be putting them into the actual air. So what we're going to do is we're going to go and have a barrier between where we have the heat and between where we actually have the room air, what we're going to be taking inside. This is going to be a component that is called my heat exchanger. And my heat exchanger simply looks like this. We're usually going to see these as being cast iron tubes, just because it's a relatively easy type of metal to make into complex shapes. We take the cast iron. That cast iron is going to go and have all of the heated sooty air. So I'm just going to draw this as being over here. We see we got gas coming in. We call this section the manifold. The manifold is going to go and provide a place for us to light these burners. These burners are going to go and provide heat. And they're also going to go and have soot because they're burning gas over there. We don't want that soot to get into our mainstream, so we take all of this, we run it through here, and as it goes through here, we force air. We force our cold air. This is going to be my return air that I have over here. We force my return air over top of this, and then the return air, as it goes over top, is going to go and pick up heat, and then it's going to pick up more heat, and then more heat, so that by the time it gets all the way out here, it's going to be fully heated. What we're seeing inside of our heat exchanger over here as well is that the heat exchanger air is going to get cooler. As it works through that system, it goes from being really, really intensely hot down here to becoming cooler and cooler. We bleed the heat off into that system, and then by the time that we're exiting the stack over here, all that we're exiting with are going to be my products of combustion and with a relatively cooled air. They are going to be fairly efficient. They're not great, but we are going to be able to strip most of the heat out of our air and into my return air. I'm going to point out as well that we are usually going to go and have the fan in the return section. It's not good for electrical motors to get heated up, so we are going to go and take the cold air and we're going to run that over top. These are usually going to be a type of motor that's called a TEAO. That means totally enclosed air over, so it's cooled by the air passing over. We take the cold air, we run it through the fan, and then we push it out to the side over here. There is going to be a requirement with these as well that we do also introduce a little bit of external air into our system. If I take a look at this, you can see that the way that it's drawn over here, all of the air that is coming out of my system is going back down and into my system over here. It's coming from up top there. This is coming from up top here. So what you can get is you can get really great efficiency because I'm going to have the air. It's going to be a little bit cool, but I'm going to reheat it. It's going to get a little bit cool. But what happens at the same time is we're going to be picking up, dust and pollens and gases and carbon monoxide and things like that. Carbon dioxide, I guess it should be. I don't know what humans breathe out. Can't remember. CO. This is not biology. I could not tell you right now if it's carbon monoxide or carbon dioxide we breathe out, but we breathe something out, and if we have too much of it, it's bad. That's, that drowning feeling when you build up too much of it inside of your lungs. What you would want inside of a house like this, though, is that there has to always be an introduction of some fresh air back into that. These are sometimes going to be done through external fans. I don't know if you have done standalone dwellings, but you're usually going to go and have that one exhaust fan that's going to have to be on a humidistat timer. Upstairs, that's going to go and run cyclically. The whole point of that is that that thing is going to, every once in a while, it is going to go and run, and it's going to go and take out a certain amount of CFM, cubic feet per minute. So the number of minutes it runs is going to go and define the number of CFM, cubic feet that's going to take out, but it's going to pull a bunch out, which means that a bunch of others are going to go and leak into other areas inside of our house, through doors and windows and cracks, etc. But it's going to be fresh air that's going to be full of oxygen, etc. It is way healthier for you to go and do this, every once in a while, just to go and open up all the doors and windows in your place and take out all the old air and, let in some new one. You just feel reinvigorated by it, right? All right. That's our furnace and our heat exchanger. Let's talk about the controls for these. Controls for these are going to be broken down usually into a line voltage and into a low voltage side. Now there's two drawings. Both of these drawings are going to be the exact same. This one shows more or less all of the components in position for a standard forced air furnace. This is going to be an old style forced air furnace that's going to be running off of a pilot light. And it shows a couple of components inside of here, like my burners and my gas lines over here, gas valves, etc. It's also going to go and show, some thermostats that I'm going to have over here, overheat relays, and my heat exchanger section itself that is going to go and have a couple of thermostats. This one is really useful for seeing where components are going to be. I see that I have got two thermostats that are going to be up top over here. We're going to look at the controls of this after on the other diagram. We'll do the controls off of that one, but let's start by looking at this. I see I've got two thermostats that are going to be inside of the heat exchanger. One of them is going to be used to turn on the fan once it gets hot enough. So when we're calling for heat, we want this thing to get hot enough. Then we're going to kick it on because we don't want to push cold air around. The other one that we are going to have over here is going to be used to shut the system down. It's going to be a safety. Anytime you see safety, it's usually talking about a shutdown. I'm also going to see another component over here. This is going to be my thermostat inside of the room. This is where I am trying to go and heat up the area. So I'm going to have a thermostat which is going to act as a switch inside of here. They're showing these little black and white things which are standing in for bimetallic strips over there that are bending to make and break contact. So thermostat is inside of the actual room. I'm going to have an overheat relay and a blower control relay that are all going to be part of the actual furnace. They don't really clearly delineate where the furnace starts and ends, but the furnace itself is going to go and contain all of this stuff over here. All that the furnace has when you buy a furnace is it has got a duct in, that's my return. It's going to have a duct out. That's going to be my supply. And then it is going to go and have power in that we are going to go and take in. Actually, I guess I should maybe even draw this one like that because it's just going to be in like that. We're going to bring power in 120 volts usually because it's a low amount of power that we're actually using. We're not doing electric heat over here. We're going to have duct in, duct out. I was trying to write supply over there. Why don't I just write that out as supply duct. Power in, and then we are also going to go and have thermostat out, which is going to be these ones over here. That's it for your connections. All the rest of this is going to be contained inside of the actual unit itself. These things over here, the safety valve and the main valve, we're going to explain those in a second, but they're going to be gas control. The gas line itself is also going to be brought in as a single one. The rest of this stuff inside of here, the main valve and the safety valve, are going to be provided by the manufacturer. Let's take a look at, sorry, wrong one there. Let's take a look at the actual control diagram over here. Let's start with the safety valve. The safety valve is simply going to shut off gas. It's going to prevent us from having any gas there if we don't have a pilot light. For those of you that don't know what a pilot light is going to be a small flame that is continuously burning along the side of a manifold. Let's go and draw this over here. We're going to call this thing a manifold. Manifold is simply going to be a place where I'm going to have mixed gas and air. It's going to have a bunch of little holes inside of it. Think about like a barbecue or something like that. And then what you'll have is you will go and have a pilot light that is just going to be lit and sitting right here down by the end of it. So something is going to be continuously lit and running over at this end. It's like having a lit match that's sitting there waiting. That lit match is waiting until we turn on the gas flow into this duct. Once we turn on the gas flow into this duct, it's going to fill up with gas, and there's going to be gas that's going to start coming out of each of these individual little jets. This first jet over here is going to go and light, and you hear that sort of noise, as the rest of it, this one lights, which propagates to this one, which lights, etc., all the way across. That's going to light up there. If this pilot light was to be out, for whatever reason, that the pilot light was gone, and if we were to introduce gas into here, that gas would just leak out. We would end up with, natural gas that would be leaking into a house. It's obviously going to be, poisonous and dangerous. We don't want to have that. So what the pilot light does over here is the pilot light is going to be the thing that actually ignites, converts it from, dangerous gases into, useful heat. If the pilot light goes out, we need to know about that. And so the pilot light is going to go and have its own standalone electrical circuit. And it's going to be working with this device called a thermocouple. A thermocouple generates voltage by heat. So what we do is we take the thermocouple, and it's going to be this little copper probe. We bait it inside of the pilot flame. It needs to be inside of that flame. And then as long as this thing is hot enough, it is going to be sending out a tiny little bit of voltage to my safety valve. No more than a couple of volts tops. That tiny little bit of volts is going to go and keep that safety valve open, so that gas is then able to go and run through there. If for whatever reason that thermocouple over here would lose its flame, it would no longer generate any of this, and that safety valve would close. And the safety valve is always in line with the main gas valve. So even if I were to be calling for gas to come into here, the safety valve would be saying, nope, I'm shutting you down because I cannot read that we have got a pilot light over there. Pilot lights do go out, if you get backdrafts or anything like that that come into a system, all of that can get, easily blown out. You'll also have times where you're going to go and build up a lot of ash that is going to go. The natural gas does build up small, fine gray ash. You'll build some up on what is referred to as the gas orifice. That's going to be the tiny hole that this thing comes out. So if you build too much gas or ash on there, then you can't get enough gas out, and so the pilot light's going to be too small and weak. Therefore, the thermocouple won't have enough voltage. A good cleaning once in a while is always a good thing. Sometimes, you'll see actual gas furnace technicians, they'll clean out the things with small pilot bits. Don't drill them out yourself, because it's a very regulated size of hole that these things have. But you can definitely clean the ash off if you have a problem with the pilot light continuously going out. Also, just make sure that it's inside here. And in some cases, you'll see small shields as well. The shields are just designed to go and bend over to force the flame over top of that. All right. That's our thermocouple. We'll just look at that over here on this one. We see that the thermocouple, if I'm just going to go and highlight the line, the thermocouple is this section over here, and it runs with a wire down to the safety valve. And if it doesn't sense that the pilot is lit, it is going to go and block off all the rest of the gas flow into there. Okay. Let's talk about the rest of this now. Now that we have covered the safety aspect of it, we see that we have got 120 volt that is going to be brought into our furnace, and then that 120 volts is going to be placed in line with a blower motor with a control relay. We see that we're also going to step down from that 120 volts down to a value of 24 volts, and then that our 24 volts is going to go through 3 separate rungs that we are going to have over here. Let's start by saying what turns the system on and off, and we know the thing that turns the system on and off is going to be a wall-mounted thermostat. So if the temperature is high, looking at this thermostat over here, if the temperature is high, this thing would be open. Start with this thing being open. Right now, if that was going to be open, I would have nothing pushed through to my main gas valve over here. If I don't have my main gas valve lit, I'm not going to have any flame. And if I don't have any flame, I'm not going to be able to go and create enough temperature to close the blower control thermostat, right? The blower control thermostat is going to be this one that's up top inside of there. So this is going to be off as well. I'm also not going to have enough temperature to go and trigger my overheat thermostat. Overheat thermostat is also up inside of the heat exchanger over here. So I'm going to be with both of those sitting off at this point. Nothing is going to be operating. The only thing that is working at this point is going to be that safety valve. Let's go and call for heat. So we're going to start by closing off the wall thermostat over here. When the wall thermostat closes off, it completes a circuit, right? We see that we can now get current flow that is going to be able to go through this normally closed and up to here, which means that my main gas valve is now going to go and open. When my main gas valve is going to go and open, it is going to go and introduce gas into the chamber, and it is going to go and light all of our burners. Okay, we'll just stick that big flame over there to stand for all of our burners being lit. So right now that has just happened. It has let the gas in, we've lit the burners. The rest of this has not done anything yet because these are all based upon these two thermostats that we are going to go and have over here. What happens is as this heat builds inside of here, it is going to be starting off inside of this heat exchanger. And the first thing that is going to go and close is that my blower control thermostat is going to go and close. This thing is going to go and close usually about 130 degrees Fahrenheit. We call it 54 Celsius, but most HVAC happens in Fahrenheit, just for point of reference. So we'll close that thing at about 130. In other words, it is hot inside of the heat exchanger. So once we have reached that temperature, 130 Fahrenheit on over there, this is going to go and close inside of there. When this closes, we complete another line over here. And so my blower control relay is going to go and get energized. At that point, when I energize this contactor over here, it is going to close this relay up top over here, which is going to go and turn on my blower motor. So now I've got a blower motor that is running. I see that I've got current running through here, and I see that there's a little bit of current running through what is referred to as the anticipator resistor. The anticipator resistor, if we look at it on the actual drawing over here, let me just erase a few things, exists over here at the actual thermostat area. And what the anticipator resistor is designed to do is it is designed to prevent temperature overshoot. It runs a little bit of current through it, which creates a tiny little bit of heat. That's what resistors do. As we run that little bit of heat over top of it, that heat activates our thermostat a little bit early. That is all it's there for, is early activation of the thermostat. So I'm going to be running a little bit through here. That is going to be a tiny little bit of heat that is going to be going over to my actual wall thermostat component itself. This is all good though. We're going to go and continue to run all of our gas through here. Our fan is going to be on, pushing the hot air throughout the house, etc. And eventually when the house reaches temperature, our thermostat would go and open. When our thermostat would open, it is going to go and drop our main gas valve. So this section over here, we'll kick that open. It's going to drop our main gas valve, which is going to shut this down over here. My fan is going to still continue running though, because this thing turns on at 130 degrees, but it's not going to go and turn off to about 90 degrees Fahrenheit. So it's now going to go and continue pushing air through until this thing gets down to 90 degrees. At that point, this is going to go and open up, which deactivates this, and in turn deactivates the blower motor. The blower is then going to go and shut off at that point. The last section that we haven't talked about was just this rung over here, which is going to be for my overheat thermostat. And all that my overheat thermostat does is it prevents me from getting to too hot and dangerous of a condition inside of here. If I take a look at this, I see that it's once again going to be inside of my heat exchanger. If for whatever reason my fan has failed to come on, I would not be able to go and evacuate all that heat that I have inside of here, so this thing could get to dangerously high temperatures. So blocked duct or a blower motor that has gone out, either one of those could lead to dangerous temperatures. What we would want it to do is we want it to just go and shut down everything that's going to happen inside of there. Let's just go and do a quick run through one more time, but this time we're going to go and trigger the overheat thermostat. So we're going to start with the system at rest. At rest, we see that my wall thermostat itself is going to go and start, initially high when the temperature is high enough, but then this thing is going to go and fall down, 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 down until eventually it is going to close. When it closes, remember this is regular operation we're showing over here, it is then going to go and open the main gas valve. When it opens the main gas valve, we are going to go and turn on our main burners. So the main burners are going to come on. The main burners are going to start heating the air inside of my heat exchanger. Once the air inside of my heat exchanger gets hot enough, my blower control thermostat will close, which is then going to go and turn on my fan. At the same time as the fan goes on, it starts preheating my thermostat through the anticipator relay over here. So this is normal operation. Let's say now that we've got a physical problem inside of this thing where somebody has gone and blocked off the hot air supply, okay? I don't know. Something's happened. We've got the hot air supply has been blocked off, and as a result, we cannot go and push air through here. And so now we're starting to go and get to dangerously high temperatures inside of here. Those dangerously high temperatures are going to be hit by this high limit. The high limit does go very high, by the way. You're going to be going 200 degrees plus. Usually these are set at a standard of 220 degrees Fahrenheit. So I'm going to go and have this rung over here when it reaches that value of 220 degrees Fahrenheit, because I had everything blocked off, it's going to close. When it closes, it is going to go and power up its relay, and we see that its relay is this one over here, which is the normally closed. When we power up a relay with a normally closed, the normally closed would have to go and open. That is going to go and drop out that rung over there. So my main gas valve is going to go and shut off over there. What we will see is that it does not shut off our blower fan. So our blower fan is still going to be able to try to clear that heat. We get dangerous amounts of heat, 220 degrees inside there. So it makes sense that we would still want to try and clear that out. This thermostat over here will not open until we drop below my 90 degrees Fahrenheit that I'm going to have. As we start dropping back down, eventually this thing will go and drop back open. It depowers that. At that point, this thing would be cleared to go and close up again. It's a safety on our system. Your module lists a couple of areas, or a couple of ways that these things can go and, fault. Room thermostats that are stuck closed. If I've got a blower motor that is refusing to run, the motor is shot, or the belt that goes from the motor to the fan, most of these are belt driven, it has, been thrown off or broken or something like that. Or if I'm going to go and have that insufficient airflow. Any one of those is going to allow us to get to way too much heat that we are going to go and have inside of it. All right, let's continue on through the rest of the furnace components. Then we'll take a pause. We'll break to another video for the last section of this one, but we still got a few more components that do go into furnaces. Let's talk about this one over here, which is going to be my electronic air cleaner. We've talked about electrostatic fields. Back when we were taking a look at the beginning of capacitors back in line A1, we talked about electrostatic fields. And we know that like charges are going to go and repel, opposite charges are going to go and attract. An electrostatic cleaner is sometimes known by its industrial name of a precipitator. You'll hear that term as well. What it does is it tries to remove dust and pollen and dander and things like that out of your air itself. And so we will go and take our air in. Over here we've got the dirty air that's going to be coming in. We are going to go and have a pre-filter just to take out the big chunks, the pieces of cat hair and things like that you don't want to necessarily run through here. That pre-filter section over here will go and just physically remove them. It's actual screening. But then what happens is we pass it through this section over here, which is going to be an ionizing section. What an ionizing section is going to be a high voltage section. Okay, remember how we have to always have complete circuits? We're going to go and have a high voltage. We're talking about into the thousands of volts over here, 20,000 volts, things like that we are going to have inside of these sections. I'm going to go and have a high voltage section over here that's going to be a positive. I'm going to have another section over here that is going to go and be a negative. And these are going to be DC high voltage sections. That high voltage positive over here, as my air goes through here, it is going to go and charge my air to become positive. Any particles that go through, not the air itself, the gases don't want to charge in the same way, but the actual pieces of, lint and stuff that do make it through the pre-filter, they're going to charge through here and they're going to go and become positively charged. Now this whole thing is going to be a grid. It's usually going to just look like a piece of chicken wire or something like that. So all the air flows through it, no problem, but in doing so, all of my pieces of dust and pollen become positively charged. They just brush up against, they pick up a positive charge. We send them over to this side on my collecting station over here. I'm going to go and have positive and negative sections. And the positive sections, those are going to be the long bars over here. are going to go and repel my dust particles. My dust particles are already positively charged. These positively charged dust particles are going to get repelled by this, drifting along the air current. They're going to get attracted towards this, and so they're going to go, and they're just going to stick right up against that plate. And if you open these up, you're going to have a really fine, loose layer of dust that you're going to see on them. All it is doing is it's ionizing the dust, and it is going to go and create, in the doing so, it is going to go and create these particles that are charged, and they stick to it. You do have to take out your collecting section once in a while, and you usually just have to shake it off, tap it off over top of a dustbin or something like that. And then all of the dust itself is going to go and fall off. Some of them can be washed, depends upon how they're built, etc. But because we're working with high voltage, never assume you can wash anything that's going to be a high voltage component. Clean them off with compressed air, someplace that's going to be outside, obviously with the dust mask on or something like that. Do not ever open these, though, when they're operational. There's nothing to see. You cannot see the electricity. You're not going to be able to see the dust particles. It is going to be absolutely anticlimactic to open it, and it's going to be highly dangerous because we have got high voltage DC sections that are going to be inside of here. The other problem that we are going to go and have is we're going to go and have free radicals, ozone, where we are going to be breaking down and recombining oxygen, and we create ozone. We've all heard about the ozone layer, which protects us from the sun, etc. This ozone is also really useful as a sterilizing agent. So when we have the high voltage, we create the ozone. It's a sterilizing agent because it is so incredibly destructive. We'll use it to wash fruits and vegetables and stuff like that. It evaporates, it doesn't stay on them, so it's nice, it doesn't leave any residue, but it destroys lung tissue when you breathe it in. So if you open one of these up, anytime you've got a high voltage precipitator and you have got ozone that is going to go and build up inside of here, you're going to be in danger. Usually the ozone stays inside of here because ozone is going to be ionized air, which means that it's going to get attracted to one of these two plates as it goes through these. But if you open it up, you now provide a place for that ozone to escape, and it can cause health issues for you. So don't do that. All right, humidifiers. Humidifiers are, we don't have a picture of a humidifier, but they're going to be mounted, once again, inside of your main duct line. We don't use them as much over here. Some really dry climates will use them just to go and keep proper humidity inside of the air. Usually it's just going to be like a paper drum that rotates through and evaporates water off or something like that. Last one that we're going to have is going to be an electric duct heater. Electric duct heater is not commonly used inside of residential applications, although they do sometimes get placed inside there. And usually these are going to be for far end heating, where I have got, maybe I've got like a big rec room over top of the garage, and it's a long ways away from the furnace, and the air that gets there is actually pretty cool. It's not, all that useful. What you'll do is you'll cut one of these into your duct heater, you will interlock it, and all it's going to be is an electric heating element that is going to go and take your somewhat cooled air. It's supposed to be hot air, but it's cooled down because of the distance you're going. As you force it over top of there, it is then going to go and heat up. Usually these are going to be more inside of a three-phase commercial type of system that we are going to go and see these, where we're going to be able to individually turn these on and off. In fact, inside most of our HVAC systems, we're going to have radiators that we're going to be able to choose whether to heat or to cool. But inside of a residential application, just inside of really large ones, you might go and see these electric duct heaters. If you do have them mounted, they should go and incorporate some sort of a sail switch, also referred to as a airflow sensor, that is going to go, and if there's no air being pushed through, it's going to prevent this thing from operating. Plenum heaters, last one that they talk about, is a less common one. Plenum heaters are going to be installed right above my furnace over here. So I'm just going to go and take this one. My plenum is going to be the heated section that's going to be up at the top over there. We stick them directly above a gas-fired furnace, and they're designed to go and work in tandem in places where we just can't keep up, particularly northern BC and a lot of our other provinces. A lot of people heat their houses off of fuel oil, kerosene still. They're going to have large tanks. They're going to get these things filled up, every couple of weeks, and then they just burn that fuel to go and continue to heat their place. In some cases, if it's cold enough outside, the heat generated by the fuel alone is not going to be enough, and so we provide a secondary makeup type of heat, which is going to be basically electric resistance heating elements installed above there. They do not go and act as your primary source. They're designed to be used in conjunction with. these. All right, that's going to be it for our HVAC section that we're going to cover in this video. We're going to start another video because this is going to be kind of our basic residential one that we've only gone through over here. We do need to go and hit another one that's going to go and cover the rest of these components and alternate types of systems.